I want to find the area bounded by these two functions. I've got x equals 3y and x equals y squared minus 10. So you may already be familiar with the fact that if you're finding the area between two functions, usually if the functions are given as y equals f of x and y equals g of x, something like that, then you integrate the top function minus the bottom function to find the area in between. Here I've got the functions written naturally as x equals a function of y. So instead of thinking of it in the top to bottom version, the way that we usually think of it, I'm going to think of this as left and right. So when I integrate, instead of going from the top function to the bottom function with respect to y, I'll go from the top function to the bottom function with respect to x, which means I'll pick the right function minus the left function. I'm not sure exactly what this looks like, but let's just make a quick sketch of this. X equals y squared minus 10 is pretty easy. It's like a parabola that opens up and is shifted down 10, except it opens up, instead of in the y direction, it opens up in the x direction. And instead of being shifted down 10 in the y direction, shifted down 10 in the x direction. So if this is negative 10, then the graph looks something like this. Then x equals 3y. I normally think of this in terms of y equals something. I know it's linear, the powers are 1, so this is a line. This would be y equals 1/3 x if I divide both sides by 3. So it has a positive slope, but the slope is small, it's 1/3. So it will look something a little bit like this. So the thing that I'm looking for is this area. If I try to do this by integrating with respect to x and picking a top function and a bottom function, there's a problem. Over here it looks fine. There's a clear top function and a bottom function. But once I get past this intersection point, the top function and the bottom function are both that parabola. So I don't want to do it that way. I want to go horizontally. And just to give you a quick reminder, this means that instead of doing Riemann sums to get to my integral that have vertical rectangles, I'm doing horizontal rectangles. And those horizontal rectangles, instead of having a width of delta x, they'll have a width of delta y. And so I'll be integrating with respect to y. I want to find these intersection points so that I can tell what my bounds will be. When I'm integrating with respect to y, I'll have this rightmost function minus the leftmost function to give me the area in between. So let's find the intersection points first. Force both of these to be true at the same time to grab those 2 points. So I can set x equal to x. Now I've got a quadratic equation. I'll move everything over to one side. And if I can factor that, that would be nice. I would need two numbers that multiply to negative 10 and add to negative 3. Negative 5 and positive 2 will do that. So now the solutions to this equation are y equals 5 and y equals negative 2. That's helpful because that gives me the bounds on my integral these rectangles need to start down at y equals -2, go all the way up to y equals 5. And again, I'm doing the top function minus the bottom function, but thinking along the x-axis instead of the y-axis. So the top function is this line, x equals 3y. I don't need parentheses. And then I subtract off the bottom function. If I happen to switch the top function and the bottom function, then what will happen is I'll get the exact same final answer, except that I'll have a negative value instead of a positive value. So if that happened, if I accidentally grabbed the wrong one, I'll just take the absolute value of the answer at the end. You should always get a positive answer for the area between two curves like this. I'll take the antiderivative. Notice I need to distribute this negative, so this is really 3y minus y squared plus 10. I use the power rule. Three halves y squared minus y cubed over 3 plus 10y. Plug in the bounds and simplify if you want to get down to a simplified final answer. The main ideas to this were find the intersection points, try to figure out which graph was on top and on bottom. Also, it was helpful to sketch this just so that I could figure out whether I should do integration with respect to y like this or integration with respect to x. If you're working with really simple functions, you may not need to sketch the graph, but sometimes it's really helpful to sketch the graph. Once I figured out what was on top and what was on bottom, and I had my intersection points, from there it's just working out the problem by finding an antiderivative, which at this point we're very comfortable with. You can go ahead and work it out and compare your answer with mine if you'd like to. Four over 2 is 2, so I get a 6 there. I'll have a minus a negative 8 thirds, so positive 8 thirds. I guess I'll interpret everything in terms of sixths, since that's my least common denominator. I've got a negative 200 over 6 here. Combined with this, it gives me a positive 25 over 6. And then 36 plus 16 is 52. 120 minus 52 is 68. So I believe this is what I have inside of there. And then when I combine those, looks like I have 93 over 6. since 9 plus 3 is 12, that's divisible by 3. I know I can reduce this. I can pull out a 3 from the top and the bottom. So when I divide by 3 on top and bottom, I get 31 over 2. Or, I know that this is the same thing as 15 and 1/2. So 15.5. If I got that incorrect, feel free to let me know.